Hi, and welcome to a Calculus 1 video on derivatives as a rate of change. You might also see this as rates of change in the natural and social sciences. And that's because we're going to look at our derivatives in application settings. What does this mean? So if we have a typical cost function c of x, that might be something like the cost to produce maybe 100 items is, let's call it $800. That is a total cost to produce all of those first 100 items. So we could make generalizations and talk about an average rate of change and say that on average is costing me approximately $8 per item to produce. Now again, that certainly is an average. We know that would not be true for the first thing that you produce, right? It's going to cost a lot more. Now, marginal cost, though, is very, very different. So my C prime of 100 is not going to be a number like 800, well, hopefully. It might be a number like 6.2. What that is saying is if I want to produce one more unit, whatever I'm producing, it will cost me approximately $6.20. So that's below my average and possibly maybe below what I'm selling it for. So maybe I keep producing. It's one piece of information that businesses can use about when to continue production or when to halt production. So my marginal cost just tells me, since that's my instantaneous rate of change, right, x equals 100 or an input of 100, it's telling me my instantaneous rate of change about right there is about 6.2. So if my slope was 6.2, that means I rise 6.2 for every one I run over. We're also going to study position, velocity, and acceleration. So most time you will see it as an S for position function, but not always. S is any height, or it could be a horizontal distance at any time t. We'll talk about labels here in a second. V is your velocity function, or first derivative of s, so we could also write it as s prime of t. And acceleration is your a function, typically defined as a. It is the second derivative of s, or it's the first derivative of velocity. And if we look at labels, maybe this will help explain why. If we talk about a typical miles per hour, where your output is miles and your input is hours, then we can go ahead and label these. Well, the position function is just your original function, so that's just going to be your output. So maybe this is in miles. Then my velocity, since it's an instantaneous rate of change, is going to be change in y over change in x. Right? Again, it's an instantaneous, but I'm going to look at my output label over my input label. So what would those labels be? Well, that would be output of miles per input label of hour. And again, I recognize we usually write mph, but for this I'm going to show you miles over hours so you kind of understand it that way. Acceleration tells you how quickly is your velocity changing. Is your velocity increasing or decreasing, etc. So it's a rate of change of the previous output. So it's going to be miles per hour squared because it's miles per hour. So let's take a look. We are going to look at a projectile motion problem in great detail, but some of the algebra or computation I will fill in as we go, and I'll also share with you why some of the directions are written the way they are. So let's start reading here. For 4.95 seconds, I'm going to highlight that because that's going to be important. A particle moves in a straight line according to the position function, where t is measured in seconds, so there's a label. That's my input, right? You're inputting t. Your output is f of t. And f is measured in feet. Answer the following questions. Answer all problems using exact values. I'm going to put an exception to that, right? And then graph to verify. So what I'm going to say is most of the time we're going to be able to round to, let's say, 3 decimals, but there's going to be a problem where I'm going to require exact values. So number 3, we're going to require exact values. So some of the others will go ahead and round. So let's look at number 1. What is the position of the particle at t equals 0, t equals 1, t equals 2, and t equals 4.95? So you are calculating f of 0, f of 1, f of 2, and f of 4.95. Now, you can certainly leave our yellow f function the way it is, but I think I would definitely take a minute and do a rewrite of f so that I could combine like terms and maybe get it a little bit more usable for derivatives. If I don't have to use product rule and things like that, I don't. So let me do a rewrite here. Okay, so there I have another alternative to my f of t. Again, if you're not sure of your algebra, you can shove in any number to the original and to mine and make sure that those are the same values. So now let's go ahead and use our technology to help us. This problem we're going to go ahead and round to, let's say, 3 decimals. Okay, I used the table feature personally on my calculator, but you can do your computation by hand if you choose, but that's how I did mine. Now, it is important that you understand the label of these. What is the position is talking about the output just directly, and that was measured in feet. So all of these should be so many feet. So I'll go ahead and label. And then I want you to really understand what is happening here. So at time 0, we are starting at 0 feet. At time 1, we are now at 3 feet. So we've gone 3 feet. So 1 second, right, we've gone 3 feet. Here's kind of my start. And then 2 seconds later, I'm 22 feet away. So now I'm over here. But then at 4.95 seconds, so as time is going on, I'm only 1.114 feet from where I started. So what happened? Well, I went pretty far, maybe even farther than 22, and then I turned around, right? And then at 4.95, I only ended about 1 foot from where I started. So I had to have turned around at some point. This happens on your running software, like if you use a MAT220 or something like that, that tracks your runs for you or your walks or whatever. Let's say you start at home and you go out for a run and you end at home. Well, if you just look at where did you start and where did you end, you haven't gone anywhere. But if you look at how far did you go out and then you turned around and how far did you come back, maybe you ran 8 miles, 4 miles out, 4 miles back. But if you only look at where did you start and where did you stop, then it looks like you've run 0. I certainly would want credit for those 8 miles, so I would want to show the turning around. Now something else is important is why are we talking about f of 4.95? That was a big part of the problem to begin with. Remember we bolded that in blue? The first part of this problem says for 4.95 seconds. Any guesses on what that tells us? That actually tells us the domain of my entire problem. It tells us that we only know this position function for these first 4.95 seconds. So I'm going to say my domain is actually 0 to 4.95. We're not going to look in negative time, and we're not going to look beyond 4.95 because this function might not model my distance. Okay, number 2 says find the velocity of the particle at time t. So the velocity of my particle I will call v of t. So that is the first derivative of my function. That's just power rule, so we should be very good at that by this point. What is the velocity of the particle at the same times 0, 1, 2, and 4.95? So I will write I'm finding v of 0, v of 1, v of 2, and v of 4.95. And again, I'm going to use my calculator table feature to help me find these values. One thing to note, if you're using the table, make sure you go ahead and hover over any number because it's only going to show you, 3 or 4 decimals or 3 or 4 values at a time. So you might not see all 3 decimal places. So I just hover over that number and then it shows me what it is. Okay, so now I need a label. So what would the label be of my velocity? Since velocity is a derivative or instantaneous rate of change, it's going to have to be a rate, something per something. So my output was in feet and my input was in seconds. So these are all feet per second. And then let's talk for a second about how you can have a negative velocity. Well, all that means is that at that point in time, you are moving backwards at that speed. So speed is always going to be a positive value. It's the absolute value of velocity. So maybe I'm traveling at 1 feet per second, but the negative gives me the direction of traveling backwards. Okay, which makes sense because remember we had to turn around at some point. So that might be your coming home, so to speak, or turning around. Number 3, when is the particle at rest? So I need to take my velocity and I'm going to set that equal to 0. You are at rest when you are not moving. So that's when your velocity is 0. So we need to figure out an exact form how to solve this. Hopefully we remember from a college algebra course that we can at least use synthetic division to help us. This doesn't look very factorable from the beginning. So I'm going to look at my p's over q's, so my 1's over 4's. So all the factors of 1, which is just 1, over all the factors of 4, 1, 2, or 4. And again, you have plus or minus all of these. So you can certainly graph and take a good guess at what would one of those zeros be, and then I can use synthetic division to help me. So for example, maybe I think negative 1/4 is a 0. I'll use synthetic division, so negative 4 is the coefficient of my cubed term, 15 is the coefficient of my squared term, 0, and then negative 1. Carry down, multiply, this is your multiplier out here. 1/16, negative 1/4 times 16 would be negative 4, add down, multiply, add down. If you get 0 as a remainder, that means that is an answer. So I know v of t is 0 when t equals negative 1/4. That's one of the answers. And now I have a quadratic, so I will use quadratic formula. I'm going to go off to the side to do that. Here's the solution using quadratic formula, and this is why the problem said exact in the beginning. I wanted to see if you could get these exact t values because these are going to be used throughout the problem. So I'm going to reference the approximately 3.73 answer as 2 plus square root of 3 and the 0.268 answer as 2 minus square root of 3. So hopefully you remember how to solve an equation that is not necessarily quadratic from the beginning because it was a cubic function, and then we just use synthetic division to break it down to a quadratic. So the 3 answers that I have for when does v of t equal 0, so when is that blue function right there equal to 0, is when t equals negative 1/4, when t equals 2 plus square root of 3, and when t equals 2 minus square root of 3. Now before I circle these, let's think back to our original discussion of domain. We are limited to 0 to 4.95. So this is not actually going to be talked about. So I have 2 plus rad 3 seconds and 2 minus rad 3 seconds because those were both within the 0 to 4.95 domain. Now the question becomes, when is this moving forward? So now I'm looking for where is v of t positive? Well, I know where v of t is equal to 0, so I'm going to create a number line here for velocity, and I label my number line. Anytime I do a number line for position, velocity, or acceleration, you're going to have to label them so you know which is which. I'm limited 0 to 4.95, so put any domain restrictions that you have on your number line. Then the 2 plus rad 3 was about 3 point something, but I'll just put it about right here. And the 2 minus rad 3 was about 0.268, but I need room to write in between 0 and that number, so if you label it, it must be so. So this was about 0.268, and this was 3.73 or something. Okay. So now what I need to do is take any number here in this blue section, so from 0 to 0.268, so something like 0 0.1, 0.05, 0.19, 0.2, something in that domain between 0 and that 2 minus rad 3, and figure out if my velocity is positive or not. Keep in mind that's what you're looking for. Where is my velocity positive? So I'm going to fill this chart out now by looking at a graphing calculator, and I'll show you the table. Okay, so in y1 I do have the function, which right now we're on velocity. And now I'm going to type in some of these numbers that are in that number line so I can see whether my velocity is positive or negative. So I'm going to use 0.1 as something that's in between 0 and 0.268. I'm going to use maybe a 2 or a 1.5 or something for the next section. And then the last section, I'll maybe just use a 4. And so all I'm looking for are these numbers positive or negative. So I see negative, positive, negative. The other thing that you can do is you can limit your window 0 to 4.95. And all I'm looking for is when I'm graphing this velocity graph, am I above or below the x-axis? Because that's what it means to be greater than or less than 0. Are you above or below that x-axis? So you can see I'm below, so it's negative values. Above, so positive, and then negative. So it's negative, positive, negative. So on my number line, I just write a negative, a positive, and a negative. So when is the particle moving forward is just when you're positive. So it'd be between 2 minus rad 3 and 2 plus rad 3. You write it in interval notation. Don't actually include those endpoints because that's where you are at rest. You have stopped at that point. You're not moving forward at the same time that you're resting. Okay, looking at the next question, find the total distance traveled by the particle on the intervals 0 to 1, these are time intervals, and 1 to 2, which is larger, and y. And we can talk about that y throughout the course because you can also start talking about your velocity at that point, etc. So find total distance traveled. This goes back to the if you're going to go run and you start at home and you end at home, does that mean you didn't go anywhere? I hope not, right? I want credit for every step I took. So maybe I went out 4 miles and came back 4 miles. I've traveled 8 miles. So I need to make sure I think about direction as well. So normally what I would say is you can just take the distance where you're at. So my function in this case was called f. So normally I could say you could just take f of 1 and subtract f of 0, and that's your total distance traveled. Because if you started at 5 feet and you moved forward the whole time and you ended at 8 feet, start at 5, end at 8, you've gone 3 feet. You could subtract those. But if you've turned around in that interval, you can no longer say f of 1 minus f of 0 because you have to figure out how far did you go out and then stop, how far did you come back. So I'm going to look at my velocity number line that we did above. I turn around, right? I'm going backwards and then forwards. I turn around at 0.268. So I have to go I have to break this up and go 0 to 0.268 and then go 0.268 to 1. Okay? So I'm going to find f of 0.268 and subtract f of 0. And I want to talk about distance in a positive way. So I'm going to make sure I take absolute value of that number. And then I'm going to add that to f of 1 minus f of 0.268. Again, absolute value, so you can keep your distance positive. So again, let's use our technology to help us find these values, some of which we already found above. I already know f of 0 because I found that above to be a 0. and I already know f of 1 because we found that to be a 3. So really the only thing I need to calculate is f. So keep in mind you're on the original function, not on velocity. F of 0.268, or that 2 minus square root of 3, is negative 0.177 if I round to 3. Negative 0.177. Don't take the absolute value of individual terms. What happens is if you started at positive 3 but ended at a negative number, you actually went farther than 3. So I went 3.177 here, and I went positive 0.177 there. So we'll add those two numbers together. So I went 3.354 feet within that first 1 second. Now if I look from 1 to 2, 1 to 2 is in this middle interval up here on my velocity window, or on my velocity number line. I don't turn around in between 1 and 2. I'm going positive in the positive direction or forward the whole time. So I can just say f of 2 minus f of 1. And again, I'm going to take absolute value of that answer because I want to talk about distance in a positive way. So f of 2 we did find above. That was 22. F of 1 we also found above. 22 minus 3 is 19. So I went 19 feet from t equals 1 to t equals 2. Obviously the 19 feet is larger, and we can look at why, especially as we start looking at those graphs. Find the acceleration of the particle at time t. So that is the first derivative of velocity. So if I look back at my velocity function from number 3 here, and that is when it's set equal to 0, but I can still see it. So if I do the derivative of that, I get negative 12t squared plus 30t. That's all that question was asking for. Now, when is the particle speeding up or slowing down is a really sort of loaded question. What we're asking you is, because of this accelerator or because of this acceleration, is the acceleration causing you to go faster or slower? So I want you to think of an airplane for a second. If there's an airplane in the air flying and its engine speed says it's traveling 450 miles per hour, that's what the engine is saying, or that's what their speedometer is saying. Well, what if the wind is coming from behind? It's called the tailwind, and it's making you go faster by 25 miles per hour. Your actual speed then is 475 miles per hour. The acceleration is speeding you up. It's going with you. Versus if you have a headwind and that wind is coming at the front of that plane, it's subtracting from your speed or slowing you down. So I want you to think of it in that way. Is the acceleration causing you to go faster or slower? So this also happens on a river with currents, right? Whether you're traveling with the current or against the current. So we need to figure out, where is my acceleration equal to 0? So let's solve that equation. Pause the video if you need to. So what I have done is solved when is the acceleration 0, and then also copy down my velocity number line from above. And what we're going to do is we're going to put this acceleration number line right below it so I can look at these two at the same time. I still have 0 to 4.95 as a domain restriction, so I would include that there. T is equal to 0 for acceleration when that is 0, so I'm going to change that to a parenthesis so I don't include that on any of my answers. And then t equals 5/2, which is 2.5, so it's going to be in between here. Now what you're going to look at is figure out the direction of your acceleration. So figure out if it's traveling in the positive direction or negative direction. So I'm going to put in some number in between 0 and 2.5, so something like a 1 or a 2, into my acceleration function. There we go, now I can see it. And then I'm going to put in something larger than 2.5, so something like 3 or 4, and see what my signs are for that acceleration. Okay, so I've completed my acceleration number line, and now you're just going to compare. From 0 to 2 minus rad 3, I'll carry this down here. Your velocity is negative, So you're traveling backwards, but the acceleration is traveling forwards. So your velocity and your acceleration are in the opposite directions, so you are slowing down. So let me write the answers out here, speeding up and slowing down. They will be intervals. So the first answer that I have is an interval of slowing down. So 0 to 2 minus rad 3, I'm slowing down. Then, if you can see, they are both positive. My velocity is positive and my acceleration is positive in this next section here. So from 2 minus rad 3 to 5 halves, or 2.5, however you want to write it, I am speeding up. And again, you don't want to include any of these boundaries because that's where it is 0, so you're neither speeding up nor slowing down. Then lastly, here's this last interval. So this is negative and negative if you want to transfer them over. So then I can see that I am positive velocity, negative acceleration, so they are in the opposite direction, so I'm slowing down again, and that would be from 5 halves to 2 plus rad 3. And then the very last one, I can see they're both negative, so even though I'm traveling in the backwards direction, the acceleration is going to speed me up. So I can say from 2 plus rad 3 to 4.95. Now here's the kicker too. 4.95, it is a bracket. Even if you look at the number lines that I've created, you can include 4.95. That was just a domain restriction from the beginning. So that number line can take a long time, but what if we wanted to know just this very last question here? Are we speeding up or slowing down at 2.7 seconds? Well, 2.7 seconds would be just after 2.5. So I'm somewhere in this section right here that I'm highlighting in pink. Well, I have a positive velocity and a negative acceleration, so I could say I'm slowing down. But why do I need that whole number line just for one value? You don't. So you could look at it algebraically or graphically. So here's the numeric interpretation. What is your velocity at 2.7? What is your acceleration at 2.7? So I'll fill those in. I filled those in, and really all you needed to know is that velocity at 2.7 is positive, acceleration is negative. The last way that you can tell is just physically to look at the graph. So let me show you both graphs. I'm going to put velocity and acceleration on the same graph. Okay, so the blue function was my velocity function. This red is my acceleration. So what I can see is that acceleration in red is positive all the time until you get to that 5 halves number. Then it's negative, and that's exactly what we found. Velocity, however, in blue is negative, positive, negative. So at 2.7, you're about right here as an x value. The blue function is positive, but the red function is negative, so you could see that positive and negative value there as well. Anytime where the graphs are both below the x-axis, you're going to be speeding up, or both above the x-axis, you're speeding up. And anytime they're different, one's above and one's below, you are slowing down. I hope you found this conversation on derivatives as rate of change helpful, and thanks for watching.